I want to make sure we've got main effect and moderation effects squared away, because those are the types of effects that are going to continue to pop up in all models from here on out in perpetuity. No matter how complex those models get, we're going to have main effects and we're going to have moderations. And when we get to path analysis, we're going to be putting main effects, moderations, and mediations. So if we're still mixing up main effects and moderations, and we're not recognizing where slopes change and where slopes don't, that's going to prohibit you from interpreting effects in the models that we do in the next few weeks. And it's going to prohibit you from interpreting effects in your projects that you're doing for the end of. Those are the most important. The little tiny details I care less about, mostly main effects and moderation slopes. All right, so we've got an evaluator who's working with an after-school program, and they're interested in the effect of program funding on student success. After collecting data, centered continuous predictor and dummy-coded state with California as the reference group. Using the parameter estimates for her model, below is the equation. It's unstandardized because you've got an intercept there. What's the very first thing I'm going to do? It's only been a week. What's the very first thing I'm going to do? Draw my model. So I've got student success score predicted by funding, which has a slope of 0.6. The first dummy coded state, which is 0.02. And the second dummy coded state, which has a slope of 0.07. And I can put my intercept over here. Remember that New York line and that Minnesota line can only take one of two values, 0 or 1. So what's the expected student success score for a program in California with average funding? Well, California is 0 because it's the reference group. So that would involve putting a 0 here, a 0 here. And what's the average as the centered value? 0. So it's also putting a 0 here. What am I left with? 4.56. 4.56. What's the expected student success score for a program in New York with average funding? The only thing that changes is New York. It gets a 1 because it's New York instead of California. So it's 4.58. What's the slope of the line depicting the relationship between funding and student success for students in California? 0.06. Is there anything hitting that slope? No. Which means no matter what, is this a main effect or are we going to see any moderation? There's no moderation in this model. We're always interested in the main effect of funding on student success considering state. We got California, Minnesota, and New York together, and y'all might have different relationships between funding and student success. I don't really care for this model. For this model, I want to figure out one relationship that works the best amongst all of you. And what I estimated was that 0.06. So no matter what, 0.06, 0.06. When we only have main effects, the slope doesn't change. Questions at all? A researcher is interested in whether the relationship between job stress and organizational commitment is moderated or depends on industry. Wow, 6 was a really nice giveaway since it's in the prompt. Does here. The relationship between job stress and organizational commitment depend on industry. That's it. What did you find in 1 to 2 sentences? So these were generally pretty strong. I think the one thing to be careful about is making sure that if the main effects are relevant, also that they get reported, not just the moderation. So for this one, if you get stuck reporting moderation, the easiest way to do it is just go line by line. If you go line by line, you can't miss anything. So if we say for nonprofit organizations, as job stress increases, actually, let's do for-profit first. That's a better story. For for-profit organizations, as job stress increases, organizational commitment goes down. However, for nonprofit organizations, as job stress goes up, organizational commitment does not take as much of a hit or does not decrease as much. One thing to be careful about, a lot of you said for nonprofit organizations, there's no relationship between job stress and organizational commitment. You know that. This line here has somewhat of a negative slope. Yes, it's very slight. And I don't doubt that if you ran a simple slopes analysis, there is a high that this would not be significant, in which case then you could say there's no relationship. Remember that visually, we can never tell whether a line is significantly different than 0 or not. So be careful. You could say it appears as if there's none to slight relationship, or there's very little relationship between job stress and organizational commitment, for that it may not be significant. You don't have any backup on the significance factor just visually. You need your simple slope to do that. When modeling interactions, centering variables serves purposes beyond basic interpretability. What are 2 specific statistical or conceptual reasons why centering is recommended? 1, it reduces multicollinearity, and 2, it allows you to use the effect of X on Y when the moderator is what? Average. It's not just that it allows us to see moderation. We can see moderation without centering. If we didn't center, then what we would be looking at in the main effect is the relationship between X and Y when our moderator was truly 0, as in nothing. Using average as a reference point allows us to then see high and low as a much better comparison point. Something around it allows us to see the effect when Z, or the moderator, is average. Developmental psychologists is interested in which of the 3 reading intervention programs, Great Leaps, Read Naturally, iGrow, most help students improve their reading fluency. Specifically, he's interested in whether reading program moderates the relationship between the number of days in an intervention program and reading fluency. Below is the equation, and you can assume Great Leaps serves as the reference group. So the first thing I'm going to do here is also draw my model. My outcome is fluency. My predictor is what? Days in a program, any program. And this is one of those ones that's moderated by a categorical that's got 3. We're going to draw 2 just to help us annotate. We're going to draw 1 here, and we're going to draw 1 here. What are those going to be labeled? We know it's not Great Leaps because Great Leaps is our reference group. So we're going to do Read Naturally and iGrow. We're going to label before we ever touch our lines, because then our lines will be easy. So we know that this intercept and this slope can only exist if we put in what value for everything else? 0. And what does it mean to put a 0 in for everything else? Your Great Leaps, you're the reference group. So right away, I can label 3.02 and 30.23. And I can even go over here, and I already know my whole equation for Great Leaps. It's y equals 30.23 plus 3.02 days. Let's go ahead and add these. We're going to want them. Right. What values can go in here? 1 or 0. That's it. Which means if they're a 0, they go away. And if they're a 1, where do they get added to? The intercept. So for Read Naturally, we've got 1.32. And for iGrow, we've got negative 0.75. And then for our moderator terms, for Read Naturally, we've got a slope. No, we've got to change the slope of positive 3.4. And we've got to change the slope for iGrow of 2. Let's finish the other 2 that we can label ABC. So let's do Read Naturally first. Y equals 31.55. So 30.23 plus 1.32. And then the slope is 6.42 days. Okay? And then our last one, iGrow, we've got y equals, what's the intercept? Someone tell me. Has it in my phone? Can't do math. Brady, do math. What is it? 29.48. Confirmed?
Yes.
Thank you. What's the slope?
1.20.
There we go. So labeling is really easy. What's the steepest line? Actually, the easiest way might be to be, where does each one start? That's even easier, I think. Who starts at the bottom? Who starts with the lowest reading fluency at this axis? iGrow. And they have the flattest slope. Then who's next? Great Leaps. And then the steepest slope and the starting point that's highest in fluency, Read Naturally. We've finished questions 10 through 12. So 10, what's the equation between days of intervention and reading fluency for students in Read Naturally? Here it is. What's the simple slope between days in the reading program and fluency for students in iGrow? There it is, 1.2. What's the predicted reading fluency score for a student who spent an average number of days in Great Leaps? There it is, 30.23, because an average number of days would be plugging in a centered 0. One thing to be careful of, I saw this on a few exams, is just the logic check. If you're working with, and this is different because you've got B's here, when you're working with betas, even if you're working with B's and you put down a slope of 31.55, that should be a trigger for you that that's probably not. Does this value actually represent a slope or not? The relationship is 31. No, that doesn't make sense. And then this one, a local elementary teacher unfamiliar with stats is interested in your finding. In 1.2 sentences, share what you found. This one is a great example where the main effect also matters. So what's the story here? There's kind of two stories. Some people were read naturally is the best program. Yes, that is an important piece. Why is it the best program? Why is it the best? Say it louder.
The shortest amount of times.
Good. You can't forget that we're not looking at the main effect of program. We're looking at how program moderates or changes the relationship between days spent and fluency. So the baseline is, as you spend more days in a program, your fluency goes up. It doesn't matter which program. They all go up. To go up faster if you're in the Read Naturally program. So both of those components are really important for interpreting what happened. If you just say, if you spend time in a program and it goes up, that doesn't actually get at the moderation. It's very easy to focus on these only and say, hey, Read Naturally is the better program. Kids in Read Naturally can read more fluently. Only at a specific point in time. Questions on this one? Oh, I love post-break class. It's my favorite. Okay. Social psychologist is studying. This one's easy. What's a centered income score for a person whose income is average? 0. All right. Social psychologist is interested in how receiving compliments impacts a person's self-esteem. She hypothesizes that source of the compliment will change that relationship. So compliment to self-esteem moderated by source. Using the following results, create the equation predicting self-esteem from compliments as moderated by source. Note that family member serves as the reference group. So people actually did fairly well on this. There were 2 trends. I'm going to write out the whole equation first, and then I'm going to show you the 2 trends. And to save time, I'm just going to copy it. You got y equals 5.97 plus 0.52 compliments minus 0.64 boss minus 0.62 friend plus 1.13 boss compliment plus 0.45 friend compliment. 2 issues were forgetting the slope for the reference group. So don't forget, and I would suggest that when you're doing this, you want to put out the terms of the equation or draw the model. So if we redraw this theoretical model the way that's helpful, it would look this. Complement to SE, friend, boss. How many arrows do we have? 5 arrows, which means we need 5 coefficients and an intercept. So if you only had 4 coefficients, if you use this model, you should have missing 1. What am I missing? I'm missing this main path. The other big issue was sign. So a lot of people had the coefficients. They added where they were supposed to subtract and subtracted where they were supposed to add. The only thing there is you just have to double check. If you start with 5.97 and you try to add 0.64, you don't get 5.33. You get something higher. That's it. Just a double check. Those are small. Again, I think that's a function of I'm stuck in plug and chug mode, not I'm stepping back and evaluating, does this equation actually represent what's happening in this research? Too much in stat student land. So here we have simple slopes. The effect of stereotype threat on academic performance moderated by frequency of praise, particularly for high school students who are newcomers to the US. What is the null hypothesis of the box t-test? So the null hypothesis of any box t-test that belongs to a coefficient is b equals 0. No relationship. In this particular instance, that t is testing which b? The simple slope, which simple slope? It should be a whole sentence. A simple slope is a whole sentence. What is the simple slope this t is testing? Kayla. Good. I'm going to say that for people online. Kayla said the relationship between stereotype threat and academic performance when praise is low. Good. So this is not telling us yes moderation, no moderation. This is telling us, is this line in yellow flat or not? This is what happens after we already there's moderation. You can see it. And you can really there's moderation because that slope is negative and significant. What about this slope? Is it significant? When praise is high, what happens? I'm not going to play charades. What happens?
There's no relationship between stereotype threat and academic performance.
Good. There is no relationship between stereotype threat and academic. Good. It goes away, which means if these lines are different, one is negative, one is flat, there's moderation. So then using the results, how do we holistically explain our findings? We need to say, hey, when praise is high, what's the big headline? If you work in a high school with newcomers, praise them. When praise is high, there is no impact of stereotype threat or the impact of stereotype threat on academic performance away. That association or on academic performance, that association goes away. The big error here was 16, that people were saying that there's no moderation, whereas that this is actually just testing the simple slope. Questions about 16 or 17? Questions on it all? All right, bye, Lorraine. What is the overall classification success rate of her model? Number 18. Other than a teeny tiny rounding error, everybody got this. Okay, why? Because it's here. So 68, you could say 68.33%, 68%. Could they say 0.68? You get that? Probably. Rader's a nice guy. 68%. According to her model, what's the strongest predictor of whether or not someone will review their subscription? Provide evidence. What do we use in binary logistic regression for determining strength? Z and Y. Standardized. We don't have a beta. The odds ratios are not standardized. Here's a question. So what's the strongest Z? It's pages read the week before. So here's the question. Is this sufficient? Pages read week before, Z equals 1.99. First of all, nope, it's Z equals 2.00 if you're rounding. Is that sufficient? What do I need? I need a p-value. This came up in another place too. A coefficient without a p-value can't be interpreted. Why? I want us to think about this one. We're on autopilot, no autopilot. Why can't a coefficient be interpreted without a p?
It's any different, 0.
Good. What is a coefficient is a ratio of something to something, effect to error. We just looking at the coefficient, we don't know how much error there is. Without the p, we have no insight into whether there's tons of error or a little bit of error. So just giving the coefficient, you can have a coefficient that looks awesome, a beta of 0.4. If that beta of 0.4 is because you have, check this out. What about this? You've got a line that there's tons of error in it. That beta is the line of best fit. It's the slope. If you have a lot of error, you're going to see that in your p-value. So you can never report a coefficient without its p-value. This happened also in the output question. That's why I'm hard. All right, manual access 50 pages. His brother Sergio, these are my brothers-in-law, access 53 pages. Assuming they were the same age and have the same average number of pages accessed over the past 10 weeks, who's more? Well, we have to look at what odds ratio. So we've got odds ratio of 1.03, or if you wanted to carry it all out before you multiplied, that's fine. So who's more to renew? Well, the odds ratio is above 1. So by definition, Sergio's more to renew. How much more is he to renew? This was the tricky one. How do we interpret that odds ratio? For every one more page read, somebody is 1.03 times more to renew. How many more pages did Sergio read than manual? What do you have to do? Multiply by 3, right? 1.03 times 3, whatever that is. Based on the results, do you suggest any changes that would improve the model's classification success? Provide evidence for your suggestion. What in the results tells you what the next move should be? There's something in here. Teresa, age is not a significant predictor. So by putting in a non-significant predictor, you're decreasing the classification success of your model. You're using something that doesn't predict to predict. Are there other things you could do? Totally. And some people were like, take age out. And also here's a bunch of other things you could do. You want there, and then try to avoid, this is a general, when you're writing a manuscript, try to avoid what I would call default suggestions. Things, increase sample size. Like, sure, we could always increase sample size, or use better measures. You want to have actual rationale in your results or your study for the suggestions you're making, rather than kind of broad best practices in research.
I was wondering, like, doesn't taking out a non-significant variable, it doesn't necessarily always increase the classification success rate, or is that?
It would be the first thing I would try. So trying to predict an outcome from something that's not significant is basically, I'm forcing a decision by your age. If I stop using your age and I only use the two things that are most predictive, I should be more accurate. Is that the same question?
Similar line, don't we have model that when we ask significant predictor, it decreased the accuracy?
So remember that the accuracy is a binary decision. So it can happen, not in any measurable way. So that's an important distinguisher, is when you're talking about odds ratio or strength of a predictor, that's literally how predictive is this thing. Because remember, we're not predicting, what are we predicting? What's the outcome? What's the units of our outcome that we're actually predicting? Logits first, and then what? Probability. So probability is continuous. What we ultimately want to do is be able to predict the probability that you're going to renew. So that's when we say what we're trying to increase is, can we better predict the probability that you will renew? Classification is a binary decision. Yep, you'll renew. Nope, you won't. So underneath the hood, we have to set a threshold of probability that at this point, is it 51%? Is it 53? Is it 55? Is it 70? At some point under the hood, you're setting a threshold to this person's a renew, this person's not. And you can actually play an R to change that threshold if you want. So you can actually, let's say you were doing something disease binary outcome. You might want to set that threshold higher so that you don't actually classify until you're really sure that probability is really high. The distribution we're predicting in Y is probability. Synthesize the results. Pages read in the previous 10 weeks and pages read before are the strongest predictors of whether someone is going to renew. Pages read the week before is the really cool pings before articles before they're up for renewal is probably the best way to get people to renew. The more they're reading before their renewal reminder, the more they are to renew. By the way, I'm not trying to trick you. It's not secret newsroom executives that are also stats. I won't try to trick you on this one. All right, I got to keep going. We got more important stuff to do. All right, this is the expertise. I love this study. This is a real study. Valuing expertise is important for modern life. When people have a problem, they need where to turn to. However, experts can be vulnerable to a particular problem of much that they may have the illusion that they know more about a topic than they actually do. Never happens in academia. This type of overconfidence is called overclaiming. So overclaiming occurs when people claim that they something that's actually impossible to because it's not real. So it's when you the capital of Sharambia, which is a country that does not exist. So to test if experts are susceptible to overclaiming, this study recruited 202 individuals from online pool, and they had each person complete the following: overclaiming, accuracy, and FIRNA, which is financial literacy, which measured their self-perceived. This one measured, which measured actual. So which model best predicted overclaiming? In this case, we are looking at model 3. I'm just going to go through these answers for time's sake. We nailed this one, model 3. Why? Because it explains significantly more variance than model 2. Delta R squared equals, you really don't rounding, y'all. P equals 0.033. Hey, it's fine if you said 0.007. That's cool too. I graded this question. I accepted this. Lest it be that you would never share results this, because this does not actually tell you anything about what's going on. Does it demonstrate that you have the skill? The reason I'm saying this is because in D, we're moving into project land. So really, the ideal answer for this is what was in model 3? That has this explains more variance than a model that just has this. Use your variables. That's what you're studying. I get it. For time's sake, that's fine. I gave it to you. How much variance in overclaiming is explained by your best model? 71%. According to your best model, what variable has the strongest effect on overclaiming? Accuracy. Beta equals negative 0.72. P-value. And then according to your best model, how much unique variance in overclaiming does your strongest predictor explain? You need to square your strongest predictor. There's 4 possible answers here depending on where you round it. 52%, 52.45, 51.84, depending on where you rounded. Don't forget that when you are looking for unique variance explained, you're squaring your beta. And then we have our moderator example with perfectionism predicting psychological distress. And we're hoping that self-compassion helps alleviate the effect of perfectionism on psychological distress. Based on the correlation table, how much variance in distress can be explained by self-compassion? We're taking the Pearson R between those two and squaring it. Again, there are 4 possible answers depending on your creative rounding. 28%, 28.98, 29, 29.16. Choose your own adventure. Does self-compassion moderate the relationship between perfectionism and psychological distress? Provide the best evidence. Yes. Again, I got a lot of this. Really, it's yes, because a model that explains psychological distress from perfectionism, self-compassion, and their interaction explains more variance in distress than a model with just the main effects of compassion and perfectionism. If you just do this, you just get really far away from the research fast. You forget what you're actually looking at. In model 2, the unstandardized regression coefficient is negative 7.89. Explain what that means to a clinical psychologist unfamiliar with statistics. This was not meant to convey that clinical psychologists are not familiar with statistics. Some might be. I happen to some that are great at stats. So we've got, let's put our model down. Perfectionism, distress, self-compassion. In model 2, the unstandardized regression coefficient for self-compassion is negative 7.89. Don't forget that an interaction term is flippable. So this model is exactly the same statistically as that model. Why? Because under the hood, what we're really regressing is perfectionism, self-compassion, and that. That's the statistical model. So it's no different. These are the same. So if we're interpreting negative 7.89, I have to use this version, easier conceptually to understand. That's the relationship between self-compassion and distress when perfectionism, visually, it's when perfectionism does not touch it. It can't hit it. It can't impact it. It can't change it. If it changes it, that 7.89 is going to change. So what's the only value that perfectionism can take on where it's not going to hit it? 0. And what is a 0 in centered terms? Average. So for every 1 unit increase in self-compassion, someone with average perfectionism's distress will go down 7.89 points. If you just said hold constant, that's not true, because if I plug something else in here, that's going to change that slope. Huge concept in moderation. This one's still confusing, not from a memorizing where do I say constant and where do I say average, from a conceptual point. Why does it have to be average in moderation versus it can be constant when I just have a main effect model? Go over that this week, because that's going to make interpreting path models and mediation models tough. We only keep this stuff as we go forward. In the context of this study, what does a simple slope represent? Simple slopes are always a relationship at a particular, you could say it's the relationship between perfectionism and distress at a particular level of self-compassion. You could say it's the effect of perfectionism on distress when self-compassion is high, average, low. Any of those is fine. What is the relationship standardized between perfectionism and psychological distress? For someone with average self-compassion, that's just going to be the original beta without the impact of 0.22. What's the standardized relationship between perfectionism and psychological distress for someone high in self-compassion? So if we have 0.22 minus 0.07, that's the moderator term. The moderator term is negative 0.07, and we get a resulting slope of 0.15. And then in no more than 2 sentences, explain your findings. You need to include something about how the relationship between perfectionism and distress is dependent on or moderated by self or someone unfamiliar, depending on self-compassion. The relationship between perfectionism and distress is always positive. If you looked at the simple slopes, they're both significant. It's just that that relationship is a little less strong when you're high in self-compassion. So it is a buffering effect in the sense that my perfectionism has less of an effect on my distress when my self-compassion is high, but that relationship goes away. Okay? Good. Any other 308C? I know I said this 5 times. I'm not trying to sound a broken record. I need us to not think about this split between C and D as a real split. Yes, the university requires me to break things up in modules. That's the only reason there's a split. We are really just picking up where we left off. Nothing we just covered is going away. It's all staying, despite what break might have suggested. So mediation helps us explain an observed relationship between a cause and an effect, a predictor and an outcome. It explains why, or some people like to think how X and Y are. Here's that example we looked at with moderation. Newborn sleep quality impacts job performance. Rather than saying what it depends on, that's moderation. This is a cause and effect. So my newborn either sleeps or they don't. I see that. Then I show up at work and my performance is high or low or somewhere in the middle. The question is why? Why do those things have a relationship? What could explain that? You're not sleeping. So sometimes that's a great example, actually, because sometimes we could put an observed, a behavioral mediator. Mediators don't have to be psychological. It could be newborns don't sleep. I don't sleep. My job performance suffers. I think often though, when we're researching, we're trying to dig one layer deeper into what those psychological explanations are. So why does my job performance actually suffer when my newborn doesn't sleep? There's all sorts of things that could go in here. My newborn sleep quality goes, as my newborn sleep quality goes up, then my mood goes up and my performance goes up. You always want to be able to trace the cause and effect path through your mediator. That's how you know it's a mediator. That's how it's not a moderator. Moderators are going to change this relationship. Mediators are going to explain this relationship. They're actually wildly different. So once you understand them, they're kind of hard to confuse. People confuse them because they just both start with M. I'm not kidding. I really think that's why people confuse them to start. Students. When we talk about mediation, there are different types of effects that we have to talk about. So we've already heard the term main effect. We've heard the term moderation effect. When we talk about mediation, there are other effects. And in order to explain those effects, we label the paths in a mediation. This is a basic mediation. We just have a predictor, a mediator, and an outcome. We could add other things. Here's a moderator. We could add another outcome. We're getting into path analysis. We have to learn the core of mediation before we can make it more complex. So we're just for mediation always going to stick with the basic mediation structure, which is predictor, mediator, outcome. When we have a basic mediation model, we refer to the paths by letters, and they're specific. So these are not just as labels. This is how we label paths in mediation. The path between our predictor and our mediator, we refer to as A, and the path between our mediator and our outcome, we refer to as B. I'm going to get to the first one in a second. We can actually take this model and break it up into different types of effects. In order to understand mediation, you have to understand each of these types of, these next two slides, you have to be able to really easily refer to what these effects are and how we label them. So let's dissect or pull apart mediation effects. So we start with the relationship between X and Y, cause and effect, newborn sleep quality and job performance. That relationship on its own, not accounting for the mediator, ignoring the mediator, is called a total effect. Why is it the total effect? Because it's all the ways that X explains Y. It's all the variance in Y that's explained by X. We label the total effect C, always. So it's the overall effect of a predictor on your outcome, ignoring or not accounting for your mediator. The total effect, though, of anything, it's a simple regression. Every simple regression we've ever run is a total effect. It's a relationship between X and Y without disaggregating its connecting causes. Good. We only call it C in the or total effect in the context of a mediation analysis. Does that make sense what they just asked? Anytime we're running a simple regression, that's a total effect. It's just the effect of X on Y. When we start using the term total effect and the letter C is when we're going to identify a mediator, then we use that terminology. Technically, every simple regression we've ever run is a total effect. Total effect ignores the mediator. What if the mediator is present? So if the mediator is present, this is the way I think about it. I always think about, you have a little person here. How can that little person get from X to Y? It can go from X, what would we say? Blank to that in.
Directly.
To Y, good. Or what's the other way? Indirectly to Y through the mediator. Guess what? That's what we call those two effects. Indirect and direct effect. So once we account for the mediator in the model, if we have a model that has a mediator, there's two effects. There's an indirect effect, which is the portion of the relationship between X and Y that is mediated by your mediator. So essentially, the relationship between newborn sleep and performance is not probably only explained by mood. What part of it is explained by mood? That's the indirect effect. And then the part that's left over is the direct effect. So total is ignoring the mediator, indirect is through the mediator, and direct is straight from X to Y when the mediator is accounted for, what's left of the relationship. Notice that the way we designate the direct effect is C prime, as in C apostrophe. In math terms, that's C prime. Why is it C prime? Because it's still just X to Y. It's X to Y after we've taken out the effect of the mediator completely. If I wanted to show them all on one picture, you've got C, which is the predictor to the outcome as if, so X to Y, as if the mediator didn't exist. Then we have the indirect effect, which is A and B. And then we have C prime, which is the direct effect, i.e. what's left over. We can take the relationship between these paths one step further and understand how they relate to each other. The total effect is just the indirect effect plus the direct effect. You can think about it again in location. If I'm standing here and I'm trying to get to the door, I can either walk straight or directly to the door, or I can go the indirect way. And those are the only two ways to get to the door. So together, they equal the total effect of all ways to get to the door. Same concept. The total effect, or C, is always equal to the direct effect plus the indirect effect. You can also flip that equation around in the sense that the indirect effect, if you just want that, is the total effect minus the direct effect. So if I take all the ways to get to the door and I take out the direct way, what's left? The indirect way. Same concept. So far, no stats yet, just conceptual. The letters are really important. Any questions?
One question. Can you hear me? So C prime is whatever's left over after you account for A times B. Thank you.
Yep. How do we actually analyze those effects? First of all, what do you notice that's different about a mediation than a regular regression or everything else we've run? There's one very big different thing about this model that's different from every model we ran in C. I might have even told you several times. No, everything, these are still betas. We're still in regression land. This is one model. What is different about this model? What's the outcome? There are two. Every time we run a regression, we're explaining variance in an outcome. Well, what outcome are we handling here? We have more than one. So I can't, if I was like, quick, go and put this in a regression model, go. How would you do it? Well, your instinct would, I'm gonna do Y regressed on M and X. What's the problem? What does that not cover? Boom, it's missing. What makes this different is we have two outcomes. So we cannot just run one regression equation. This model has two outcomes. So we have to figure out an approach to being able to capture both the direct effect and the total effect and the indirect effect using regression. How do we do that? And the answer is, well, it depends. Are we going to use the old school way? Or are we going to use the newer school way? The answer is the newer school way. We're going to learn the old school way first. It's not significant. If it's not significant, then we have what's called full or complete mediation. As in, if I'm standing over here and I can get from A and B, once I do that, this is blocked, as in not significant, then what's the only way to get to the door? Gotta go around, which means it's a full mediation. That mediator down there fully explains the relationship between X and Y. I can't go the direct way. But we also have the potential for it to be weaker, still significant. If it's weaker, still significant, that means we have partial mediation, okay? Meaning working memory is one explanation for why stereotype threat and performance relate to each other, not the only one. There's still a direct effect of stereotype threat of performance on achievement that we have left to explain. We have not fully explained it with working memory. Alan, go ahead.
So for step 3, do you do multiple regression? You don't have to run it again, and now you can-
Correct. Well, it's not that you just don't have to run it again. It's because you have to have this in, you have to have working memory considered in the model to what C prime is. Because this, remember, whenever you look at a multiple regression, this relationship is the effect of X on Y, holding that constant, considering this. We have to have them both in the model to get C prime. So if you wanted, you could run, if you split it, you would end up running it this. X, Y, M, X, Y, then you would have to run them both together. Because the only way to get C prime is to run it together. Otherwise, you're just getting the total effect again.
Why does it always weaken the direct relationship?
Because what is the total effect consist of? Everything possible. The total effect is the direct effect and the indirect effect together.
I guess mathematically it makes sense. Conceptually, I'm not sure. Like, why couldn't a mediator amplify a relationship?
Because it's not a moderator. It's not changing that slope. It's taking all of the relationship and it's attributing it to source A or source B. It's a lot more cutting up. That's why I use the term dissecting. The total effect is literally the total effect. That relationship is getting dissected into two parts, indirect and direct. It was sort of a piecemeal. It's sort of a piecemeal approach. We can't test this whole thing at once. When we test a model, we test the model. This is the model. Really, did we statistically test one model? No, we tested 3. We had to break down why, because we can't run one regression with more than one outcome. We can't. So we had to break this model down into different regressions in order to test all the pieces, all the paths of the model. But there are problems with this model, or this approach, I should say. So just go ahead and take a screenshot and then, so this is looking at the effect of the relationship that a child has with their parent on aggression and whether that is explained by executive. The idea that when you have parent-child relationship, the stronger that is, the stronger your executive functioning and thus the weaker or less amount of regression that you would aggression that you would expect to see. So these are they tested model 1, model 2, model 3. You can see in model 3, there's the 4 step. So steps 3 and 4 get answered in model 3. So we're going to go through this and draw and annotate and then figure out, is there mediation? And if not, and then what's the total effect of parent on child? So if you notice, I blanked out the results for model 1. That was on purpose. There are actually results hidden under here on model 1. but if you understand the relationship between A, B, C, and C prime, then you can figure out the total effect without actually needing that beta. So we're going to start by drawing it. So we have parent-child relationship to aggression, and it's mediated by executive functioning. And then what's the notation for for this path here? This is why I said if you're somewhere quiet, just you can answer you would in class.
A.
Good. A, what's this one over on the right? B. And then this one you can label, technically, if you wanted, you could draw PCR to aggression on its own and label it C, because it's really not accounting for the mediator. Sometimes shorthand, we just go this. We label one C and one C prime. It doesn't matter which one's on top. It's the idea that actually, if I were going to make any logic for which one would be on top and on the bottom, I might flip them so that you could be, this is what it would be if I chopped off everything above the line. And this is the effect accounting for the mediator. We're going to label them. So let's start with model. Model 2 is regressing EF onto PCR. So EF is onto PCR. So this is A, and we're going to label it 0.21. Even if you had the B, you want to use the betas for these again, because you can't understand strength of relationship without. In general, the only thing that Bs are good for is what? I shouldn't say the only thing. What are Bs most helpful for?
Predicting.
Good. Predicting someone's score. So in this case, predicting kids' aggression score. If you had their raw values of PCR and executive functioning, plugging those in is much more helpful with the betas, because then with the Bs, because then you can plug in the raw values. For understanding what's going on, betas are more helpful. Questions about that at all? Whenever I draw models or label results, I'm going to be using betas because they're the ones where you can quickly understand, is this a strong positive relationship, a weak positive relationship, a strong negative relationship, etc. B, to label B and C prime, we need to use model 3. So we've got this first beta here, which is PCR to aggression. And then the second one is executive functioning. Let's do that one. Executive functioning to regression is 0.26. And both of these I'll just indicate that. And then PCR to aggression is negative 0.19. Is that C or C prime?
C prime,
C prime, why?
because it's not the total, it's without the A times B.
So it's with. So this is the relationship between PCR. You can think about it just a normal multiple regression. Let's just look here for a second. Anytime you're interpreting a beta in a multiple regression, how do you interpret it? Really, the biggest limitation it overcomes is it overcomes the Sobel test problem, which is that an indirect effect is not a normal. We can't use a normal test on it. So how does bootstrapping work? Before we actually go back to the model that we're interested in, I have to teach you how bootstrapping works at its core. And we're going to learn it with just something super basic, average, a mean. We're going to bootstrap a mean. So what is bootstrapping to begin with? It's a resampling method. It's not the only resampling method that exists. When we talk about resampling, the goal of resampling, that means taking multiple samples. The goal of resampling is to make inferential. We're trying to infer out to the population, just like we do when we do parametric statistics. So when I say parametric statistics, what I'm talking about is hypothesis testing. The goal of hypothesis testing is to take a single sample and infer something about the population using a hypothesis test. The goal of bootstrapping is the same thing. It's to be able to infer something about the population. How we achieve that goal is different. We're not going to run a hypothesis test. We're going to bootstrap and then infer. So instead of using a sampling distribution that is already existed, a T, a Z, and we're going to use our own. So you'll see. So sampling distributions, and it's all the way back to the third lecture of 308A. Sampling distributions are what we use. Pre-existing sampling distributions are what we use to decide whether a null hypothesis should be retained or rejected. Parametric sampling distributions, the ones used are T and Z. Those are the normal sampling distributions. In resampling, we're going to create what's called an empirical distribution. Does anyone remember the difference between theoretical and empirical in context of stats?
An empirical distribution is discontinuous or it's spotty, whereas theoretical is a continuous line.
So that's one characteristic of the difference. What's the core difference about them in terms of how they're created?
Theoretical.
Actual data.
So the theoretical T and Z distribution, we don't create that with actual data. It's been mathematically defined for us, and we can use it to figure out where our critical value lies, our calculated value lies relative to a critical value. An empirical distribution is created with actual data, and it's our data. So we're going to use our sample data, and we're going to resample to create a T distribution that we can use to make a decision, an inferential decision about an indirect effect, a mean, a beta, whatever you want. So when would you use it? When would you use bootstrapping versus pre-existing T or Z distribution and just run a hypothesis test? When you have a really small sample size. If you have a really small sample size, you can't always get away with a T or a Z because you don't have enough people to be able to find that effect. If you bootstrap using a really small sample size, you can create a distribution that you can actually use. If you violate parametric, when you're running, for example, let's say you're running a structural equation model or something, and your data are not normal, you can use bootstrapping to overcome that. If our data are not normal, we cannot use some pre-existing theoretical distribution if it's wildly not normal. I'm talking when you're testing statistics that are not usually used in parametric. Let's say you want to know about the median. Is the median significantly different? Or you want to test a ratio. Those don't get tested. There's not, when you run a t-test, the top of the t-test is means. It's not ratios or medians. So you can use parametric when you're trying to get inferential, you're trying to infer something about the population median or the population ratio, and you can't use a normal T or Z test. When you feel it, or always, you can always bootstrap if you want. If your data are perfectly normal, your bootstrapping approach and your parametric approach are going to give you the same exact result. So let's talk about bootstrapping. First important key point, it is a technique. It is not a form of statistical analysis, and it is not a test. We are still going to have to determine whether there's an effect or not. This is a resampling approach or technique that's used, not a form of analysis. We're still doing a mediation. We're still doing regression. That's still the analysis we're running. We're just doing regression with bootstrapping. It's a technique to add on. Instead of applying a predetermined normal distribution, T or Z, bootstrapping is using our observed sample distribution as the best representation of the population from which that data came. So it's basically creating its own sampling distribution of the whole population by randomly sampling with replacement, meaning every time you take out a sample, you put it back. Actually, every time you take out a little thing, you put it back. I'll show you. Then bootstrapping estimates the confidence intervals for whatever you're interested in. If you're interested in a mean, a median, an indirect effect, a variance, whatever you're bootstrapping, it's going to give you a confidence interval around that estimate. And what do we can do with confidence intervals that is the same as what we can do with a hypothesis test?
Determine significance.
Basically, and how do we do that?
Does it have zero?
Does the confidence interval include zero? If the confidence interval doesn't include zero, then we're basically saying, hey, there's an effect here. It's not zero. So we're achieving the same result, which is we're inferring out to the population. We are not conducting a hypothesis test. Questions before I show you exactly how it works? Victor.
So just logically, if you have a very small population and you just keep testing it against itself over and over again, why does that make it significant to represent the population if you basically don't have enough information? It seems like you're supporting your own argument.
The Golden State Warriors are going to answer the question for you. Does that sound good?
Sure.
What? And then I'll come back to it if it doesn't get answered. So let's look at how bootstrapping works, and it will partially answer Victor's question. If you're talking about the demo that I'm about to show you is with 5 data points. If you really only had 5 data points, that might not be enough. If you had 10, you'll see why you actually are going to get a much broader spread of the population than what you contain in your sample. You'll see. All right, so here's how it works. The Golden State Warriors, circa 2019, there will never be a better team. These are my favorite. I've almost replaced it. I was going to replace it with something more recent. That would have to not include Iggy, and that would make me, we're going to keep these 5. If you don't care about basketball, that's fine. And I will never have a Cal team on here. So our question of interest, our question of interest is what is the average number of points that are scored in a game by the Warriors? And we're only going to use data that we have for these 5 players. Okay, that's it. We don't have all their games. We just have these 5 data points. We don't have the whole thing. So here's how bootstrapping works. These are the 5 players that we have. These are their average points per game. These are their actual average points per game. FYI, TAs, I updated it to make sure that Durant did not score 3 points on average. So these are their actual average scores over time that they played with the Warriors. And the way that bootstrapping works is this. We take all 5 players and we put their scores in a theoretical resampling bucket. And then what we're going to do is we're going to pull out the first data point. So I happen to pull out green and green's average is 9 points. Then I'm throwing green back in the bucket. My next pull, I'm going backwards. My next pull was Iggy. His average is 7 points. Put it down on my list. Throw Iggy back in the bucket. Pull my next one. I keep throwing him back at the bucket by swiping left. I need to just keep swiping the deck forward. Next, I pull out green again. Green's average is 9 points. Then I happen to pull out Durant, 25 points. Put Durant back in, pulled the next one, I pulled Durant again, 25 points. That is my first bootstrapped sample. To your question, Victor, the reason that you end up with more of a representation than what you have is because you can end up with a bootstrap sample where I pulled Iggy 5 times and the average is 7. So now I've got this really, really low value, and I can pull Durant 5 times and end up with this really, really high value. So you actually end up with more of a spread than just your sample contains. If your sample is too small, you can't overcome that with bootstrapping. You can get a much broader variance than you have in your sample with bootstrapping because you're creating 1,000 or 10,000 combinations of these values. That makes sense? So I've got my first bootstrap sample, okay? And generally, we repeat it somewhere between 1,000 and 10,000 times. So we do that. That's one bootstrap sample. I'm going to do that 10,000 times. I'm not, RS, very quickly. Unless you have a complicated model, then it's not quickly. And then you're going to plot each of those to create a sampling distribution. And from there, we can estimate the real effect using confidence intervals. So here's my observed sample. The mean across all my players observed was 16.8. Here's the first bootstrap sample we just pulled. The average was 15. All right, ESPN, knock it off. We got stats to learn. We got 15 as our average on this first bootstrap sample, lower than the observed mean. Here's another bootstrap sample. I pulled Curry twice, Thompson twice, and Green. This sample had an average of 19, which is slightly higher than my observed sample. If I pulled Durant the whole time, how did that end up in there? If I pulled that the whole time, I would have 25 would be my average. That would be way higher than my observed mean. And if I pulled Iggy all 5 times, I'd have 7, and that would be way lower than my observed mean. What I'm going to do is every time I pull a mean, 15, 19, watch, I'm going to plot it. So the first mean I pull, I plot it. Second mean I pull, I plot it. Keep going, keep going, keep going, keep going until I'm at 10,000 times. And what you're going to end up getting is a normal distribution where the middle of that normal distribution is what?
True mean, it's like 16.
16.8. Exactly.
Mean.
It's your observed mean is here. There it is, 16.8. And the samples over here is that one where I pulled 25 all 5 times. And over here is that one where I got Iggy all 5 times. And then I can build a 95% confidence interval around this, and the confidence interval looks this, 10.40 to 23.20. So if we were to do this a million times, which we did, 95% of the confidence intervals would be in this range. So we can say this with 95% confidence, roughly, that the true average of the Golden State Warriors lies somewhere in here, with 16.8 being our best estimate. Is 0 a value? No, we're only testing a mean. We don't really care about significance. A mean is a mean. It's just a descriptive stat. So we're inferring out to the population for a descriptive stat here. Here's what it actually looks. So I fed this data into R and asked it to actually bootstrap 1,000 resamples for me. And this is what that confidence interval looks. So here is that 16.8. So you can see it's not a perfectly bell curve because it's resampled. If I resampled another 9,000, if I actually did it 10,000 times, this curve would be smoother. The more you resample, the more it's going to look like a smooth normal curve. You can see the lower bound is 10.4, the upper bound is 23.2. The true population mean we can infer lies in that range. I'll take questions and then we'll keep going. Jason.
What are some reasons that you don't bootstrap a lot of time? Because why can't you just always go 10,000 or a million times until you get, is there any reason why would you not bootstrap tons of time?
What time?
Oh,
When we were running an SEM, the last model that I'm bootstrapping a mean here, or did it in a second. The last time I bootstrapped an indirect effect in an SEM model with moderation, I had to leave my computer and pick it up in the morning. So it takes time to bootstrap because it's actually resampling. And here we're resampling one thing. If you've got a whole giant model with a bunch of parameters that you're estimating, it takes a long time. So that's really the only reason why. And it also has to do with if your sample size is really, really big, you don't need to bootstrap 10,000 times. So if you were doing a mediation and sample size were not a problem, the only reason is you can't bells because it's not normal. You don't need to bootstrap as many times if you have a bigger sample.
And so is the criteria for when to stop bootstrapping always just a given amount? Because why can't you set the criteria? So I will bootstrap this until the average of the distribution 16.8. Or is that just
It
not?
will always be. You don't have to bootstrap far to get the average to regress down to the mean. That's common. 1,000 is gonna, if I do this with 10,000, I'm not gonna see a wildly different distribution or different values. It's just gonna be smoother. Generally, for posterity's sake, I would say if I were running a real publication, I would generally do 10,000 times just to be safe. If I'm running something because I quickly want to check what's going on, I usually use 1,000 because Brady just posted something in the chat, which is actually really helpful. In his old job, he used to run bootstrapped things for 2 to 5 days for complex models. You just let it go. Burkle 16, you have a question? Hey, we can.
We have a question that became a lot of questions via discussion. What happens if you have a small sample, you have an outlier in your sample? Would this significantly exacerbate that? And then what do you do about that?
No, because you're going to end up, you're going to see the effect of the outlier still. You're probably going to have a tiny bit of you'll have higher values that you wouldn't have. This would actually alleviate that to some degree because some of your bootstrap samples aren't going to include that outlier. So you'll have lower values that you would never have if you just included the outlier every time. So it can actually be that outlier is what's causing your data to not be normal, and bootstrapping would be an approach to alleviating that. So you can bootstrap, your bootstrapped distribution is still going to be normal. Do you remember the demo we did way back in A where I took you to that computer program and I showed you even if the data looks this, when you resample a sampling distribution, the sampling distribution will always end up normal. What it would require if you had a really extreme outlier is you probably want to bootstrap more times. Good question.
Thank you.
Kayla, do you have a question?
Yes, I guess I'm wondering, how is this different from fishing for a result? Because that, at least from at first glance, that's kind of what it feels.
Why?
I guess because we have this small sample and we didn't see anything and we manipulated the data to try to see something.
We did see something. We saw, here we're just estimating a mean. We saw a mean of 16.8. That's the average. We just have more information. The least accurate would be, oh, well, the average of my data is that must be it. That's the average points that the Warriors score. It's the same as my sample. That would be a very poor inference because we were working with a sample, not a population. What we did by creating the empirical distribution is 16.8 is still my best guess. Really, the real average probably lies in this range. So we aren't actually fishing for anything. We're giving ourselves a better inference about what's happening because we're creating values out in the population that we don't actually have access to. Some averages are lower than 16.8 and some are higher, and we can create those with the sampling distribution. It's not going to, this isn't a technique to find an effect because you couldn't find it because your sample's too small. If there's no effect, if we're doing this on something other than a mean beta, if there's no indirect effect, the bootstrapping is not going to make an indirect effect. It's the idea that when you get a beta of 0.44, it's not significant. Let's say you're running a model and you get a beta of 0.44 and it's P equals 0.057. By standard statistics hypothesis testing, you would have to say there's no relationship between X and Y. Do you really think that's true with a beta of 0.44?
No.
So what are some of the possible causes? Well, your sample could be too small. It's meant as a technique to better represent what's happening in the population when some limitation you've got, either normality or sample size, is prohibiting you from actually making a good inference. If your beta is 0.06 and I bootstrap that, guess what's going to happen?
Nothing.
It's going to include 0 because the tiny values are going to be in there and the confidence interval is going to include 0. And you're going to have to make the same assumption you would if you would with a hypothesis test. Remember the rule too, that if you're using a hypothesis test and your data are normal, your confidence interval is going to give you the exact same result. Remember, when the p-value is less than 0.05, confidence interval doesn't include 0. When it's more than 0.05, it does. Those are always going to reflect each other. The confidence interval isn't producing a different result. It's just not hypothesis testing. It always mirrors the result of a hypothesis test.
That makes sense. Thanks.
Sean, that's a good way of thinking about it. You're artificially creating law of large numbers. So this is what it looks like. Here, we just inferred a mean, you can infer anything. You can bootstrap anything. You can bootstrap a mean, you can bootstrap a beta, you can bootstrap a correlation, you can bootstrap a median, you can bootstrap a ratio. Any statistic of interest, you can bootstrap to infer out to the population. And then you use those confidence intervals to make an inference about what's happening. Just you would use a p-value to make an inference about what's happening. When we hypothesis test, you get your statistic, your beta, your R, whatever, and you get a p-value. When you bootstrap, you get your statistic, your beta, your R, whatever, that's in the middle, and you get a confidence interval. Notice how those allow you to make the exact same type of inference. They achieve it in a different way. One is a theoretical distribution, T or Z, and one is an empirical distribution that we're using. Because it's empirical, we can't use p-values. It's not a we don't have the probability of getting this or something more extreme, assuming the null hypothesis is true, is this, because we created the distribution. We don't have pre-established probabilities for it. So we can't use p-values. Confidence intervals gives us the same information and more. Hold on one second and I'll take your question in. You can end up with 3 types of confidence intervals. What's the same about the first confidence interval and the second confidence interval here?
Don't include 0.
They don't include 0, which means there is a relationship. It's just that one is positive relationship and one is negative relationship. This one includes 0. So the true population parameter is somewhere in this range, and 0 is a plausible number, meaning no relationship is a plausible fact or a plausible outcome in the population. So in this case, we would infer the exact same thing. We would infer by getting a p-value that's more than 0.05. It's the same inference, different approach. N.
Is there a limitation to the skew that this can overcome? I think of income or something where there's really wildly different values on the large end. If you're taking samples and finding a mean, and I have people that are making $100 million and everyone else is making $1,000, I think that then it would say that the variance is most people are in the middle, somewhere in between that. I don't think that would represent the population. I don't feel I could infer that out.
I'm looking for something really quick. Do you remember this? So there's income. Nope, still normal. It's central limit theorem. No, it will be normal still. What it will affect is the range of your confidence interval.
So make it larger. I'm less confident
Can't hear you.
in my answer.
Oh, go ahead,
To
say it
bring
again.
up this applet window.
Oh,
It starts you off with
sorry.
a default normal distribution.
I didn't realize you could hear that. I said it will still be normal. It will influence the confidence interval range.
Would it make it I'm less confident in it because it's more skewed?
Correct.
Thank you.
Yep. All right. So that was bootstrapping with just a mean. We're not interested in bootstrapping means because let's just look at them in the sample. And we're generally not interested in inferring a population mean. Though if you wanted to, you could bootstrap it. What we really want to use this for is bootstrapping relationships. So if our data are not normal and we're running a model and we want to know what those regression paths are, we want to have a better estimate, we can bootstrap. If we're running an indirect effect, which is by definition skewed, so we can't just run a Sobel's test and we want to know an indirect effect, we can also use regression coefficient. We can bootstrap betas, just we bootstrap means. It's the same process. So here's one sample. Here's our observed sample, X and Y. The relationship between X and Y here is 0.83 and the P is 0.084. Then we can bootstrap one sample. We get 0.99. It's really, really tight. And it's P less than 0.01. Here's another one. We got beta equals 0.95. P is 0.015 if you were to just run p-values on these. We can run a confidence interval on that. Doesn't include 0, and there is a relationship here. The beta is something different than 0, or plausibly not going to be 0. We can also do it with an indirect. We're not going to use this table to just calculate A times B. We're going to run it with an indirect effect. So here's what it looks like. You've got bootstrap sample A. You've got path A for each of your bootstrap samples. So the first sample, I took one person. So you're all my sample. I took you and I put your data down. I put you back in. Then I took Lisa and I put her data down and I put you back in. Then I took Hector and I put his data down and I put it back in. Then I grabbed and I got Hector again and I put Hector back in on my data. Once my sample is complete, that's my first bootstrap sample, I calculate path A, I calculate path B, and I calculate path A times B. Then I do that 9,999 more times until I have 10,000. So notice I'm resampling the whole sample first and then getting an A, a B, and an A times B. So I'm basically doing what I did in the Barron and Kenny method 10,000 times. I'm calculating both of those A times Bs. And here's what it looks like. So I just simulated this data, and this was not with a tiny sample size. This was a normal sample size. I'm bootstrapping the indirect effect because I'm interested in overcoming the limitations of bells to what is the true indirect effect and what is the 95% confidence interval around that. So the 95% confidence interval around that is negative 0.17 to negative 0.32. I can say the 95% confidence interval does not include, there is an indirect effect through working memory. The indirect effect of stereotype threat on academic performance through working memory was significant, beta negative 0.24, 95% confidence interval. Notice no p-value. Why? Because I didn't use a pre-existing theoretical distribution, a T or a Z. I used this as my sampling distribution. Remember when I taught sampling distributions, I was like, it's if you went in and pulled out a sample 10,000 times. Well, we did, for real, and we created it. And that's how we're estimating the true indirect effect of stereotype threat on academic performance through working memory. Questions about this?
Jess,
Maybe do
my bad.
hands that I can pick you off from the Zoom up top. AJ, go ahead.
So even though there's no p-value, we do kind of have something akin to a pseudo p-value with the confidence interval. So even then we would just say because the confidence interval does not include 0, almost the same thing as saying if we had a p-value of less than 0.05.
Rather than thinking about it that way, I want you to think about what you actually do know. Don't distill what you do know to something smaller than what you know is something more, which is that out there in the population, you want to know the effect of stereotype threat on academic performance through working memory. And that the magnitude of that effect is somewhere in between negative 0.17 and negative 0.32. And that the best estimate of that effect is negative 0.24. By definition, just in saying that, I told you that 0 is not there. I said, hey, it is something, and it's something in this range. Does that make sense? Burkle 16.
So the original issue with doing A times B is because it creates that skew. When you bootstrap it, I don't see how after you times out the bootstrap, it doesn't continue to have that skew. Can you explain that a little bit more?
So if it goes back to central limit theorem, which is when you have, if I had 5 values, 1, 2, 3, and 50, that's very skewed. If I bootstrap 1, bootstrap 2, bootstrap 3, bootstrap 4. Let's say that in bootstrap 1, I got 1, 2, 3, 1, and then 1, 1, 1, 1, and then 50, 50, 50. You're still going to end up at the end of the day with a normal distribution. That's that demo that I just pulled up. Anytime you have, no matter what the original population looks like, when you create it's a sampling distribution. It's what's going to be the most, you're not recreating the original distribution. You're creating the center of a sampling distribution is what you are most to get, which is the observed sample. And then in equal amount, you will be over by some and you will be under by some. And that's what creates that normal distribution. Does that make sense?
Yes.
Brady.
To completely answer the research question, if you go back to slide 64, we wouldn't have to just bootstrap beta for A times B. We'd also want to bootstrap C prime.
So you don't have to bootstrap so you're going to run, you'll still run, I'll show you in the demo, but I'll show you in the demo that you're running both together. You're going to get all of your estimates. You're going to get the A path, the B path, the indirect path, the C path, and the C prime path. Yes.
Thanks.
I do this on the indirect effect because the indirect effect issue is what drives our need to bootstrap.
That's the hole in the logic.
But that's the hole in the logic. We're going to bootstrap all of it. Jason.
So other than just, let's just say, computational resource costs, is there any other theoretical limitations towards bootstrapping? Because this just gives a higher fidelity answer than just null hypothesis significance. Why don't we just do this for literally everything?
Well, it's not necessary. If you have a basic regression model and your data is normal-ish, you're not adding any value by bootstrapping. You're going to get the same exact result. You can still calculate a confidence interval. Remember, here's a good question to answer that. Everybody should be able to answer this question. If you can't, let's talk about it. What is this distribution that you're looking at? What is it serving in place of?
The theoretical.
This is your version of T or Z. If T or Z works, doing an empirical one is going to give you the exact same thing, just takes longer. So there's no need to bootstrap when you meet conditions of, hey, people spent a lot of time creating a T and Z distribution when our data meets a certain assumption. Let's use it. It's easy. So, and you can still calculate a confidence interval around that. So you don't need bootstraps for confidence intervals. You still get those too. So it's just unnecessary. When you start to play with more complex models and your data looks messy, I would say that for most of first of all, most of my models include some sort of mediation, but I would say almost all of my models I bootstrap. Victor.
Understand that when the confidence interval includes 0, it's not significant. Or when it does include 0, it's not significant. And when it doesn't, it is. What if it's close to 0, one of the numbers? And how close and where do you draw that line?
Good. So that is something that we talked about when we did confidence intervals. Sometimes you can end up with a confidence interval that looks this negative. What does that mean? And your beta, then your estimate's probably going to be, 0.32, something like that. What does this mean?
No, go ahead.
Go for it, Alan.
Means it includes 0 just barely. And
You're thinking a stat student. I don't want you to be like, it includes 0. Yes, I can see that. What does it mean? What did you find as a researcher if this is your confidence interval? How do you make sense of it? I wanted the effect of sleep on mood, and this is what I get. You're not going to say the confidence interval includes 0. What did you find? And the confidence interval is negative 0.01 to 0.67. How do we make sense of that as a researcher? This is how you make sense of it. The best estimate that I have of the relationship between sleep and mood is 0.32. That's a pretty meaningful beta. That's not small at all. 0.32, it looks like there's a relationship. However, the precision of that estimate, how good it is a little bit rocky. The real relationship out there in the population actually looks at somewhere between these two. It could be as high as 0.67, which is super high, or it could be 0, which means there actually is no relationship. Remember that confidence intervals are normally distributed with 0.32 in the middle, 0.67 out here, and 0.01 over here, negative 0.01 over here. So where are the most plausible values? They're here. I created a 95% confidence interval. That's pretty big. Really, if I had to say, what do I think's going on? It's somewhere, there is a relationship. The probability of it being 0, which is here, is very, very small. It's 0.06 because it's going to correspond to the p-value. It's very small. It just doesn't meet that binary decision-making cutoff we've established in statistics. It's the same as if you got a p-value of 0.057. You would have to say it's not significant. You would be, I'm going to walk away thinking there's no relationship here. You could compute a 90% confidence interval and guess what it's not going to include? 0. Some people do that. That's the same as saying I'm going to use a p-value of 0.1. There's no difference. For some reason, confidence intervals are a little bit more acceptable that way. We remember, this is a mindset shift. It's not we want to check the stats rule. Our goal is to figure out as best as we can what's happening in the population with all the limitations we've got of our sample, of stats, of our methods, everything. And so if we just use binary rules and we don't take in the whole picture, we aren't actually doing the best we can to figure out what's happening in the population. To look at this and say there's no relationship between sleep and mood would mean you are looking at one tiny piece of information, which is that 0 is not in the confidence interval. That's not good stats. Good stats is taking all the pieces of information that you have and what's our best it's an inference. That's the whole idea. We can never confirm it as truth. What's our best inference and what else might we need to do as a researcher to strengthen that inference? I would to redo this and get really solid significance or a tighter, to M's point, a tighter confidence interval. That would be great. In this study, this is what I got. I'm going to make the best inference I can of the population with what I've got. Alan.
How would you write that up? Let's say that's what you got. You got the confidence interval of -0.01.
Send you the last paper I published. It's in there. I'm just kidding. I mean, that's what I said. I said, and this, I didn't use Bootstrap in this. So I had a p-value. I was like, beta equals 0.20, p equals 0.057 or 0.06. Confidence interval looks this. I would say, according to hypothesis testing and the confidence interval including 0, we would interpret this as non-significant. However, confidence intervals are normally distributed. The probability of it being 0 compared to a value that's much higher than 0 is very, very low. So it's a stronger inference to assume that there is something going on here. We would need to conduct additional research with additional samples to confirm whether that's the case. And I have to explain it a little bit. I really can post a section of a paper that I have that did that, because you have to explain it a little bit, because if you don't understand how stats works and all you is 0, no 0, then you would look at that and be, that's wrong. If you understand how confidence intervals work, you would look at that confidence interval and be, it's way more to be something not 0 than it is to be 0. And to Victor's question of, well, where's the cutoff? There isn't one. The further negative this gets, the less I can say that. And it also depends where this confidence interval is. If this was my confidence interval, instead of 0.67, it was 0.17, well, then the 0 is still really small. I'm less confident. It's the middle of the interval is not really high. So my beta wouldn't be this anymore. So then I'm not as to push that argument. What are the two things that are going to contribute? Well, what's the one thing that's contributing to that interval being narrow or big?
Sample size.
Standard error. And what are the two things that go into standard error? There are two things.
Then the sample size.
Spread and sample size. Someone took A. Good job. Spread of the original. The more spread the data are, the wider your interval, or the more error you have. And then sample size. If you have a really small sample size, your error is going to be the next thing that I look at then is, well, clearly my standard error, my beta is pretty strong. If this is 0.67 and my beta is 0.32, then my error is what's causing that really wide interval. So then my next question is, well, what's going on in my error? Do I have a small sample size or is my sample size big? Then it's not sample size. What does my spread look like? I can look at my descriptives to see. I can look at the error for the individual paths. There's a lot of digging I can do to give meaty discussion to what Alan asked. How do I report it? Well, I report it that, then I'm going to probably discuss it a little more in the discussion section. Why did that happen? The answer always lies in your data. Cool. I love the review on confidence intervals. It's great. Any other questions about either the confidence interval piece or indirect effects mediation? So what I was writing here, which I didn't finish, is this is your empirically created sampling distribution. It's always going to be normal. Remember central limit theorem. And it's analogous to T or Z. It's analogous to the theoretical distributions that we're used to working with when our data is normal. So you're actually familiar with this study. This is the Michigan Employment Security Commission study. We did this when we were doing binary logistic regression. We were predicting whether or not people were employed 6 weeks following. We're going to use the same data set for the first demo and then a different data set for the second demo. The actual mediation that we're going to look at is, is the effect of job program to depression at time 2 as mediated by, I'm going to switch back and forth basically between this slide deck. And so we're going to read in the data and change the columns to lower. And we don't need all of the data that's in here. It's a super big data. We're going to create a smaller data set, which we don't have to, just to make our lives easier. I'm going to create a smaller data set called dat.jobs in line 65. This is a function that generates the count of missing. This is just a nice way. You can run descriptives too. I like to throw in new functions every once in a while that you can see just what they look. So this is counting which is NA. It's summing all the NAs and putting them into a object called NA count. And then I'm putting those objects in a nice table and then calling that I can see it. This is not something that you then need to blindly copy paste into your DA. If I'm giving you data that doesn't have missing data, you don't need this. This is just an easy way because I have 1,285 observations. I have a really quick way to see how much missing data I have. And I can see I have no missing data, which is nice. I don't have to do it. The next thing I'm going to do is I'm going to run my descriptives. And I added the split by treatment here because I'm just curious. I want to see, I don't need an average of treatment. Remember, treatment was either 0. I didn't do the program 1. I did the pure. I want to see the different variables parsed out in the graphs by people who did do the program and people who did it. So here we have our graphs. And we can look at our data. This is another way, by the way, obviously, if you want to see missing data, you can see it here. We've got min and max is pretty low, 1 to 3 for depression, 1 to 5 for depression at time. That's a better range. That's what we're going to use. And mastery is our mediator variable. We're going to run, we're treating it just we treat. This is still regression under the hood. Mediation is still using regression. So it's still the general linear. We're still going to look at our data through all the lenses of the general linear model that we would if we were just doing basic regression. So we're going to look at a correlation table first to see whether things are related to each other. So we've got depression at time 2 is negatively related to mastery, which is good. That's good for our hypothesized mediation. We think that people who are higher in mastery are reporting lower depression 2 scores. Notice that treatment is not in here. Why isn't treatment in here?
Because categorical.
Because it's categorical. If I wanted to see whether there's a difference in mastery or depression in time 2 based on treatment, what would I do if I wanted to quick check that?
Just have the correlation, do one table for people that went through and one people that didn't.
That won't work necessarily. You could do that. What's the better way?
Just an ANOVA?
No.
Test?
T-test. You are used to doing stats in steps. All of these are tools that I'll throw into my analysis to explore a question that pops up. If I want to really quickly check if there's a difference in depression based on whether you participated or not, I'll jump in here and throw a t-test in there just to check, to satiate my curiosity. Even though it's not part of my formal analysis, those are still helpful tools to help answer. I'm going to run my scatter plots to check for linearity. Here's job seeking and depression. Here's mastery and depression. That's that strong negative relationship. Here's job search self-efficacy and depression. And then this is going to be useless. This is 0 or 1. This is my categorical variable. We want to test normality and homoscedasticity. In order to do that, we need to create our saturated model. Just need to specify the model using LM, linear model, and then use that model to check homoscedasticity and multivariate normality. So the model that we're running in our mediation is depression 2 as our outcome, predicted by mastery and participation in treatment. So treatment is our X, our predictor, mastery is our mediator, and depression at time 2 is our outcome. So we're going to create the model, and then we're going to plot the residuals of that model and also test the homoscedasticity, test whether those residuals are constant across all levels of our predictors. So let's homoscedasticity first. Yikes, that's ugly. There's a perfect fan for you. So not a lot of error at low values of the predictor. As we get to higher values, there's a lot more spread. I'm extra not concerned about it in this case because we're going to be, it also helps a little bit with homoscedasticity. Let's look at normality. We've got a little bit of a curve, not a totally straight line. Remember that this is plotting your residuals on the y-axis relative to perfectly normal model residuals. So a perfect straight line would be your model residuals, your model error is perfectly correlated with perfectly normally distributed. Therefore, your data are multivariate normal. This is not a perfect straight line. And we can see here with the Hahn-Circular test that our data are not multivariate normal. Again, we're bootstrapping. This would be one time to say, however, we're bootstrapping our parameter estimates, which will help alleviate the issue or help overcome the issue of non-multivariate normal data. All right, let's do it. I'm gonna do program participation to depression mediated by mastery. And I'm gonna control for, because I'm a good statistician, I'm gonna control for depression at time 1. So I'm going to throw depression at time 1 in all of my models that predict depression at time 2, because then I get to control for it and I get to see the true relationship on depression at time 2, considering what people started with from a baseline level of depression. It's not part of my mediation. It's just an extra outcome that's pointing at depression at time 2. So I'm going to do Barron and Kenny approach first. So step 1 is I'm going to regress depression at time 2 onto treatment. At time, we've got depression. Predictors are treatment, and I'm always going to just control for depression at time 1, because this is going to allow me to see whether participating in the treatment has an actual effect on depression, regardless of where people's baseline was. Otherwise, if I don't include that baseline, then if you started really high in depression, you're going to still have some degree when you're done, and vice versa, and that's going to cloud my ability to see the real effect. So that's my step 1 is X to Y. My step 2 is X to my mediator, so treatment to mastery. And then in step 3 and 4, that's my third model, I'm going to run both treatment and mastery onto depression at time 2. And notice again, because I'm predicting depression at time 2, I'm just controlling for depression at time 1. It's not of interest to me in terms of a coefficient. I'm just using it as a control variable. So let's run these. All right. So first model is treatment to depression at time 2. Is it significant?
No.
No. So yes, Jason's, it doesn't matter. We don't listen to Barrett and Kenny's step 1. We just keep going. We are going to keep going. But it would be not a weird logical inference to be, oh, there's no relationship between participating in the program and depression. So why would we keep going? It's not an implausible logical conclusion. It makes sense. There's no relationship between X and why would we unpack that relationship? That relationship can be hidden depending on what mediators we're using, whether that mediator has a positive relationship with our outcome or a negative relationship with our outcome. So that first path is not that total effect. This is C, is not significant. Let's look at X to treatment to mastery. So is there a relationship between treatment and mastery? Does participating in the program have an association with higher level of mastery, job seeking mastery? Yes, it's a small beta, significant. And then our last model has both mastery predicting depression at time 2 and treatment predicting. And what do we see? Mastery is quite a strong beta. High mastery is associated with lower levels of depression at time 2, even when controlling for depression at time 1. Beta is negative 0.42. And is treatment significant?
No.
No. What effect is this here?
The full mediation.
What effect is that? What do I call that effect?
Oh, C prime.
Which is the direct, that's the label. What's this effect called?
The direct effect.
The direct effect. Good. Yep, which is labeled by C prime. So let's put this on our model to make sense of what happened, if I can find the model. All right. So there was our C relationship. There's our total effect. The relationship, the effect of participation in the program on depression at time 2. Remember, I'm controlling for depression at time 1 here. It's not in my model because it's just a control variable. That was significant. So when we control for someone's baseline depression, just participating in the program was not a significant predictor of depression. Here's our A path. It was significant. Here's our B path. It was significant. And there's our C prime path. It was not significant. Do we have mediation?
Yes.
Yes. What kind of mediation?
Full mediation.
Full mediation. So our C path is negative 0.03. Our A and B path, if we multiply those, so if we multiply negative 0.42 by 0.08, we get an indirect effect of negative 0.03. That indirect effect is the effect of jobs program. The way we talk about it is always, it's the effect of X on Y as explained by or mediated by or through mastery. It's really the effect of X on Y we're interested in. It's that mediator is the explanation of that. If we wanted to use the Barron and Kenny method, what would we want to add on?
Sobel test?
A Sobel's test, exactly. So we're gonna do that. So we've got our Barron and Kenny method, we have all our paths, and we're gonna test that indirect effect, which was negative 0.03. We're gonna test whether that indirect effect is actually significant or not. Remember what distribution Bell's using to test that.
Normal?
Which distribution? Which sampling distribution?
Oh, T, Z?
Yeah, T or Z with law of relative numbers at Z. But we're using the pre-existing normal distribution. R does not or care that our A times B distribution is not actually normal. It's going to do it for us anyway. And here is the code. You've got depression 2 is the outcome. Test mediation is the function. We're going to specify which test of mediation we want. And the test we want is here. Well, outcome is depression at time 2. Predictors are treatment number. So participating in the treatment. The mediator is mastery, and then you're able to add any covariates, any control variables that you want in that model. So I'm telling it, hey, depression's not part of my mediation, it's just a covariate. And here we get it. We have our estimate, our standard error, and our Z value, which is significant. But we don't really want to do that. Wells is running a normalized parametric test on non-parametric data. So instead, we're going to bootstrap. So the function that we're going to use is the mediate function. There's a million mediation functions out there. This actually, my favorite used to be modmed. It doesn't exist. This is an alternative. There are other ones out there that you can use. It just changes what the layout looks like. You have to specify both models, both pieces of the mediation before you can use the mediate package. So we're going to specify what is predicting mastery, and we're going to specify what's predicting depression too. So a little foreshadow into path analysis. The old name for path analysis when it first got invented used to be simultaneous equations, because what you're really running is simultaneous equations. You've got one predicting mastery as an outcome, and you've got another predicting depression 2 as an outcome. We just want them run all together. Really, they're separate regressions because you're talking about multiple outcomes. So the first one is my mediator outcome. It's treatment predicting mastery. My second is my outcome model. That's treatment and mastery. And I threw in depression here because I want that as a covariate. So I need to specify both of those, and then I need to put them into my mediate function. So my mediate function comes from the package mediation. I'm going to put in both there's the mediation predicting, and there's the ones predicting depression at time 2. I'm going to tell it how many simulations I want. I'm going to do 1,000 just because you don't need to sit here and watch me bootstrap. I want it to bootstrap. I want a confidence interval in percentage. I want a 95% confidence interval. And then I have to tell it what's my X, what's my treatment. Treat is what's my predictor, and mediator is what's my mediator. And then I need to tell it the confidence level that I want. And this is just the format of the data. So we're going to run this whole thing, and we're going to call it jobs.med. Oh, got to run the models first. Then I'm going to ask for, notice it's still taking a minute. See that? That's because it's bootstrapping. And it tells me I'm running non-parametric bootstrap in case you were concerned. That's what I'm doing. And then I'm going to ask for a summary of it. And this is what you get. No, I deleted it. Don't do that. So here's what you get. Non-parametric bootstrap confidence intervals with percentile method. You have 3 effects here. How many effects are there in mediation? 3. Total, direct, and indirect. This literally outpops total, indirect, and direct for you. So the total effect is here. Notice they also said it was not significant. ADE is average direct effect, and ACME is average causal mediation effect. So that's your indirect effect. The only thing I hate about this function, anyone know what I hate about this function? Can anyone guess what I don't about it? It's on the screen.
It's doing significant testing?
Yes, exactly. It should not be giving me p-values. I'm using an empirically created, it's creating its own p-value using that. You do not need to report the p-values. It is more appropriate to just report the confidence intervals for the indirect effects. This is one of those situations where the total effect was not significant. The indirect effect was. If I want to label everything, what does this not give you that you should still have in a regression table?
The direct effect, the C prime.
You have that. That's AD, average direct,
The
right?
total.
You have that too?
No,
Your A and B.
You don't have the individual A and B paths. So notice here you have here, this is your indirect effect. This is A times B. AD is your direct effect. That's C prime. Total effect is C. You're missing A beta and B beta because it's assuming what you really care about is A times B, not A beta and B beta. We in our tables and our figures to also label those coefficients. So if you want, you can just pull them out of the you put up here. And the way I do that is I just say, hey, give me the betas for this model and give me the betas for this model.
Excuse me, Jess.
There they are.
The estimates given in the mediate, those are standardized. In the ACME and the AD.
You can tell. Let's look. So let's run this whole thing and then we can look. 7.
Standardized?
Look, they're unstandardized.
Oh.
Bummer. I have to look. I'll have to check that. Let me look at this one real quick. Stand by. This one will be different. Oh, we can check it this way. Just check it against the Baron and Kinney. So if we look, 05, 0.007, treatment to mastery 0.07. They're standardized. Oh, you're talking about in the total effects in this one?
Yes.
0.05. No, they're unstandardized.
Is there a way to have the betas for the?
Let me see if there's an argument we can add in here, or could you look up if there's an argument that we could have in here that would standardize it? Otherwise, the really easy way is what we did in the last, I think it was the last demo, is just standardize your whole data set before you run it.
We were working on this before today. We couldn't find it. I wasn't sure if you.
Let me look into it and then I'll get back to everybody. I agree that it would be nice to have these standardized, not unstandardized. These are unstandardized here. Here it's hard to tell because they're less than 1. You would tell very easily if they were more than 1. Jason.
Do we need to interpret proportion of mediated?
Oh, thank you. So the other line that I didn't even talk about, which is because it's new, is proportion mediated. So the way that you interpret this, proportion mediated 0.87, which is rounded to 0.88, is that 88% of the relationship between participation in the program and depression at time 2 is explained by mastery. So this is a really nice one for a lay audience interpretation. It's just saying, well, how much of the effect of X on Y is explained by the particular mediator? That makes sense?
But why is it not significant?
I don't know why, because it shouldn't be. I think it's just automatically running hypothesis tests on it. It shouldn't. It's a proportion mediated. It's not, it should just give.
So if it's a proportion mediated, would you report it as 88% of whatever this could?
You could say, because if you're saying to somebody who doesn't understand stats, oh, the indirect effect is significant. You could say another way to think about it is that if you think of all of the relationship between participating in the program and depression at time 2, mastery is explaining 88% of that. It's not a number we use in stats reporting. It's more helpful for lay interpretation.
And would you also include the confidence interval interpretation for that, or 95% confident that if we run this test 100 times, this proportion will be found, or no?
Just look at the proportion versus the confidence interval. It's not
true.
Taking the value and it's applying the same exact approach that it did for relationships. It's not a relationship. This is the fault of the package.
Got it. And if we're making the APA table for this, bootstrapping
proportion mediation in it. If you're doing the APA table for this, generally what you would do, I think I have one in here for you. It's not a good example. You would include all of them. You'd include A to B, B to Y, A path, B path, C prime path, and then the indirect effects. Questions?
I think I just need time for it to sink in and then practice it.
I'm going to try one thing here. We did this, I think 2 weeks ago. What is the actual code? So to answer this question, the easiest thing to do is probably at this point to just standardize your data. If I can find it quicker, easier, a different way to just standardize, you can. All you do to standardize is you do, what's our data frame? It's called dat.jobs. So dat.jobs as data frame, scale dat.jobs. Why isn't it working? Should work for me. Hold on. What did we use last time?
I think you have to tell it which column to scale. So you can't just do dat jobs, dollar depressed to, and that sort of thing.
It's because it's not numeric. Hold on. I'm going to have to get back to you on this one. Usually you can just do this because treatment is not numeric. That's why. Let me get back on how to get the standardized versions of the mediation output.
ChatGPT agrees with the method. You just standardize the models up front.
But you could just standardize the data as a standardized model up front. And then that way, when you run the mediation package that we're using, you get all standardized estimates instead of Bs. In general, if you want to start building that into your practice, it's not a bad practice to standardize all your continuous variables to start at the very beginning always, after you run your descriptives. You always need to run your descriptives first because you wanted your means and things in raw values. And once you do that, it's never a bad idea to standardize your variables because then you're automatically getting betas every single time and you don't ever worry about it. All right, there's another one for you to play with down here. This is a portion of a research study I did on how hierarchy predicts psychological safety as mediated by social identity threat. And then I controlled for identity centrality. So you can look at this and you can run this. Folks who are doing office hours can run you through this if you want to do another example, and you can see whether that's mediated. And these are all continuous. So this would be really easy. You could just standardize the data to begin with. Jason.
Is there some kind of nice visualization of mediation as we have for
Like
moderation?
with moderation?
No, it's just the theoretical.
Because it's not changing a line. It's not changing a slope. You could still plot all those individual lines if you want, but there's not a pretty. I highly suggest if you're able to stay for the rest of office hours that you just hop into a room and do demo 2 together.